try again. All right, that looks better. It's working.
Hey.
Hey, crazy. I don't know how good the stream is.
It's fine. I do bad stream off all the time.
Yeah, it's pretty. How delayed is yours usually? Like really delayed?
Pretty delayed.
Like 5 seconds or more?
Yeah.
Yeah. It's all right. People are updating me. All right, we'll get started. So, first page, passed out in class today. Just stuff to make sure you have memorized. The reference tables, like the full reference tables, have letters. Reference table A through T. A is like STP. B are all the heat constants you need to know. I put D in question marks just because it's just units. So, do you have to memorize those? I hope not. But some of you keep forgetting what volume is and keep thinking that grams is a mass unit. So, just keep that in mind. Reference table T, no, and you've used them multiple times. Just keep in mind for gas laws, any of the gas laws, including Pivnert, T needs to be in Kelvin. Heat, you don't need to convert temperature at all. Pivnert, not on the reference table. You should know T, again, must be in Kelvin. 2 R values, you'll either get an atmosphere or a K-pop problem, so just keep that in mind. You will not be able to use a colored periodic table, so just make sure you have those regions down. You will not have to do an ion. You will not have to do an excited state. We're going to revisit that another day just because that caused a lot of confusion on your quiz last week. And we'll give that a go again sometime later in the week or next quarter. Or next week even, which is next quarter.
Oh.
What a coincidence. Partial pressure and Graham's law. So I'm just going to go over those 7 problems that was assigned in this little just kind of like what's not on the CASEL learning that you should know and be able to do. So the first one, you should be able to use the heat equations, any of them, to potentially figure out information when you mix a substance with water. So that substance could be anything. Could be ice, could be a totally different substance, could be a metal. I made a little boo-boo on question 1 here. I did not give you the specific heat of iron to solve this problem. You could always just Google that from home. I've checked over your quarterly numerous times, did not make this mistake, so you should be okay. But you can always look up the specific heat for iron. So C for iron is, iron out, 0.45. Joules, blah, 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 all those units written out. What are you laughing at? Huh? See you over there. All right, so you got a 50.6 gram sample of iron. Put it into a 104 gram sample of water at 19.7 degrees. This 19.7 degrees goes with the water. And the final temperature of the mixture is 24.3 degrees. What was the initial temperature of the iron? So this is somewhat new. We haven't actually really done an initial temperature problem. But this isn't too bad. The heat in will always equal the heat out. So the heat, since the water is increasing in heat, the heat leaving the iron is the same as the heat gained by the water. So we just need to set our 2 MCATs equal to each other and then just solve for the missing variable. So for the iron, our M was 50.6, our C was 0.45, and then our delta T is minus 24.3. Now, some of you might say, shouldn't you be doing 24.3 minus the unknown temperature, since 24.3 is the final temperature, not the initial? And usually, but based on this problem, based on the fact that we know iron is losing the heat, I don't want us to get a negative answer and then thus report a negative temperature. So just keep that in mind. And that will be equal to the mass of the water, which is 104, times the specific heat of the water, which is 4.18, and just up here because I ran out of room, times the temperature change of the water, which is 4.6. So 24.3 minus 19.7 is 4.6. I don't know what this text means. What? Is that a good thing or a bad thing? Oh, stream health is going down. Maybe. We'll see.
It's fine. It'll record.
Yeah. So from here, you just combine all your like terms, do a lot of distribution. And in this case, on the left side, you're going to get 22.77x minus 553.3 equals a bunch of numbers just multiplied over there. So you're going to get about 1999.7. Add 553.3 to both sides, and you'll get 22.77x equals 2553. Divide both sides by 22.77, and you'll get a temperature of about 112, which was our answer. All right, so whenever you mix two samples together at different temperatures, you just say MCAT equals MCAT. Plug in everything you know. You'll probably always know M and C, but plug in everything you know and solve for what you don't know. So while initially this problem presents itself as having two variables, what Q is not important because it's the same for both. So you know the Q for the water, you don't know the Q for the iron, but you don't need to do anything about that. Just based on a few questions I just got, I'm going to guess at the beginning of my stream wasn't working. For heat problems, you do not need to convert to Kelvin, because since it's MCAT, it's a change in temperature, and a change in any unit of temperature will always be the same. So if you convert to Kelvin, the difference is going to be the same as if you don't. If your temperature changes from 10 degrees Celsius to 15 degrees Celsius, your temperature in Kelvin will also change by 5 degrees. So you don't need to convert to Kelvin for these. Okay, next one. Gas law problem using Pivnert. And this one, again, is not too bad. You just have to piece together what's happening. You have 1.2 grams of some unknown gas in a balloon. You initially got this gas from a canister that was at this volume and temperature. So the temperature and volume of the canister that contains the gas is different than the temperature and volume of the room. The temperature of the room is 25 degrees Celsius, which is the temperature the balloon is in. So the gas went through a change in temperature. So we're going to have to do something for that. What is the weight of the gas in grams per mole? Assume the pressure remains 1 atmosphere throughout. Lovely. So since pressure is constant, we can ignore it for this beginning part, which is going to be a P1V1T1, P2V2T2, where the initial volume of the gas is 0.4478 at a temperature of 50 plus 273. And the final temperature of the gas will be 298 Kelvin over X. So It went from a volume and temperature in the canister to a volume and temperature in the balloon. You know the temperature of the balloon, but not the volume of the balloon. And doing a little quick and easy cross multiply and divide, you'll get 0.414 liters. Now you know the volume at which the gas is occupying this balloon. You know the pressure that this balloon is at with the gas in it. You know R, you know T. You can solve for N, which is moles, and then you can do grams divided by moles. So you got 1 times 0.414 liters of gas equals N, which is your unknown, times 0.0821 because we are in atmospheres, so not 8.314. You would do that for kPa. Times the temperature in Kelvin, and the balloon is at 25 degrees Celsius, so that's 298 Kelvin. Dividing both sides by 0.0821 times 298. So dividing both sides by 0.0821 times 298, crosses out over here. You'll get an N equal to 0.017 moles. Our final answer needs to be in grams over moles. So take 1.2 and divide it by 0.017, and you'll get your answer here of about 71. You might get around 70. Depends on how you round. So, you initially read this problem. You didn't know the volume. You knew the volume the gas was in the container, or the canister, but you didn't know the volume of the gas in the balloon, because you don't know how big the balloon is once you pump the gas in. But you know the temperature of the balloon, and you know that the pressure remained the same throughout at 1 atmosphere. So we did a P1, V1, T1 to get the volume. From here, you can get moles from Pivnert because you have all other pieces of information in that equation. And then just take your grams divided by moles, and you'll get your weight in grams divided by moles, which is what the question was asking. And that's it. And again, just to reiterate tomorrow, you're not going to get a whole lot of these like tough application-based questions. Probably like 2 or 3, because we don't have a lot of time. I don't want to make this a 2-day quarterly, that's for sure. And it's all about where are we? What do we know? What do we not know? How are we doing with chemistry generally before we worry about the hard parts of chem? So just keep that in mind. 3, partial pressure. So you have a mixture of 3 different gases. You're not given moles of hydrogen or nitrogen, but we can figure that out. And you are given moles of oxygen. When the partial pressure of the oxygen is 78, what's the total pressure? So when we do partial pressure, we got to keep in mind that to get the partial pressure of any individual gas, it's the moles of that one gas divided by all the moles of all the gases times the total pressure. And initially, we don't have this, and we're trying to solve for this. So, we need to be able to figure out one of those to move on, and luckily we can figure out this just based on all the information that's been given to us in the problem. So, to go back down to the problem, we can get moles of hydrogen, we can get moles of nitrogen, we can add that all together with the moles of the oxygen, and we'll have total moles. So, this answer here is based on the fact that hydrogen and nitrogen are what we call diatomic, which means they exist in the atmosphere as a molecule bonded to itself. So H2 and N2. I'll make sure to clarify this if there's a problem like this on your test tomorrow, because if you don't know that up front, you'll get a slightly different, much larger answer than the one I got. So, if you go to the periodic table, we're just going to look up the weights of nitrogen and hydrogen. Hydrogen weighs about 1, so I'm just going to round that down to 1, make our life easy. And nitrogen weighs, again, pretty It weighs 1 to the hundredth place, Mrs. G. We don't need your comments over there. We're pretty good over here. Nitrogen weighs about 14, so we're going to use 14 because it pretty much weighs 14.
Loosey-goosey.
So, headed on back. That's the same thing. Headed on back. We know that our given mass of hydrogen is 14 grams. And remember, we're doing H2. So the actual mass of hydrogen is going to be 1 plus 1, which is 2 grams. And moles. Our given mass of nitrogen is 84. Again, our actual mass is going to be 28 grams because 14 plus 14 is 28. And that'll give us about 3 moles. So our total moles, so if we set up our equation here, we got the partial pressure of oxygen is equal to the moles of oxygen divided by the total moles, which is going to be 7 plus 3 plus 2, which is 12, times our total pressure, which is unknown. So 78 is going to equal, I'm just going to change that into a decimal, 0.167 times the total pressure. Divide both sides by 0.167, and you will get a total pressure of, this calculation based on a little bit of rounding, 467, which is close to 468. And that's it for that one. So again, partial pressure, all about what's the total pressure, the mole fraction, multiply those together, and you get the partial pressure. You could do Pivnert if the problem gives you enough information to use Pivnert. And you can just Pivnert each gas individually because the N for each gas will be different. V, T, and R will all be the same. That being said, I did not give you a volume here. I did not give you a temperature here. So you cannot assume any of that. Therefore, you cannot Pivnert. So thank you for not doing that. 4, I can say with certainty you're going to get some problem about an isotope in math tomorrow. Might be an average atomic mass. Might be a problem like this. Might be both. Based on my calculation and the text I sent out earlier, I must have fat-fingered my calculator at some point because I did not get the answers provided on this sheet. So I'm going to cross that out. I was off by a little bit. That happens when you don't check over your work particularly closely. So lesson learned here,
Life lessons, man.
boys and girls, check over your work. Because this is a relatively meaningless and at the end of the day, not so impactful mistake. But there's been times in the history of the world where a slight miscalculation has led to billions of dollars lost and possibly lives, with bridges collapsing and space shuttles just missing the mark by a few billion miles. So just keep that in mind. What? Got a little grim?
Yeah, it took a turn.
Took a turn.
Took a turn.
You never know where these streams are going to go. That is for sure. All right, so what are the percents of these? I don't know, but we do know that the average mass the average mass is 20.18. So again, this is going to set up that x plus 1 minus x situation that we've done before. I'm just going to make 19.99 my x plus my other mass times 1 minus x equal to my average mass, which is 20.18. Do a little lovely distribution here, and you get 19.99x plus 21.99 minus 21.99x equals 20.18. I'm going to combine some beautiful like terms. Subtract both sides by 21.99. Combine these bad boys over here, and you'll get negative 2x is equal to negative 1.81. Divide both sides by negative 2. And that means your neon 20, which I designated as my X, will get you 90.5%, because when you do that division, you should get 0.905, if I'm not mistaken, which means your other guy should be 5%. And that adds up to 100, so we should be wonderful. So, remember, whatever one you designate as X, the other one will be 1 minus X. Whichever one you designate as X, when you get your answer, that is the percent for the one you said was X. So just keep that in mind, and we'll be muy bueno. Right, Mrs. G?
Muy bueno.
Oh, so muy bueno. All right. 5. I can determine the electron configurations of any element with an atomic number less than 57. So, no excited state, no ion with this stuff. Just, here's an element, tell me its electron configuration. So, when you go to the periodic table, we're going to find beautiful Ag, which is atomic number 47. Woo! There you are. And we're going to do this step by step, starting at hydrogen, aka energy level 1. So, we go 1. I'll highlight as I go. S, 2. 2s, 2. 2p, 6. 3s, 2. 3p, 6. Yes, you can use a shortcut. 4s, 2. Here comes the tricky part. 3d, subtract 1, 10. 4p, 6. 5s, 2. 4d, 1, 2, 3, 4, 5, 6, 7, 8, 9 at silver. So that's the long way. Shortcut way. Bracket the noble gas that comes before silver, krypton, and then just count what comes after krypton. So the easy, beautiful final answer is krypton 5s2 4d9. Question was posed, why do you subtract when you get to the d orbital? So, energy level 3. When you hit that energy level, the d orbitals come into play. They exist at energy level 3. So if you imagine the nucleus in the middle, and you pretend this is a Bohr model, and our electrons are at energy level 1, 3. When you hit this, the d orbitals exist. That being said, it is much more energetically favorable to fill in the 2 available at energy level 4 in our s orbitals before we start chucking in 10 electrons into our d orbitals, because it's just more stable that way. That's the long answer. The short answer is you just do it. So it's really for stability reasons. The math checks out. Someone did that math and they figured it out. And it just makes more sense from the viewpoint of electrons being negatively charged. They repel each other. We don't want to overload our d orbitals when it might make more sense to put them in a smaller, slightly less energetic s orbital first. And that's that. All right. Graham's law equation. That's the lovely square root equation on the front here, where the rate of gas 1 divided by the rate of gas 2 is equal to the square root of the weight of gas 2 divided by the weight of gas 1. Now, what you say is gas 1 or gas 2 is entirely up to you. You will get the question right as long as you keep track of what you're doing. Based on the question, since you're comparing something to hydrogen, and again, I used H2 here, you need to make sure that I think it's easier that you always put the lighter gas in the numerator on the left-hand side of your equation. So I would be comparing hydrogen to SO2 and then square root it. Because if you do it the other way around, you'll still get the right answer, but you'll get the answer from the viewpoint of sulfur dioxide, which means you'll be saying how much slower sulfur dioxide is instead of saying how much faster hydrogen is, which is still right, but you might word your answer wrong, and I just want to make sure you play your cards straight. So, I'm going to put hydrogen on top, sulfur dioxide on the bottom, which means on this side, I'm going to put the weight of hydrogen on the bottom and the weight of sulfur dioxide on the top. When I square root both of those, after that division, I get 5.63. And that's it. Quick comment on Graham's law that you guys goof on a little bit. Let's say you had a question that was like 7.2 equals the square root of 200 over x. We struggle with this idea of how to cancel out a radical. Some of you rectify that idea with by squaring it. So you're like, I'm going to square it. So if I square this entire expression, the radical goes away, the square goes away. And then you move on with your life and cross multiply and divide. What you do to one side of the equation, you have to do to the other. If you square it over here, well, you got to square over here too, you silly heads. Now you can move on with your life. With your 7.2 squared equals 200 over x. And cross multiply and divide. So just keep that in mind. Just keep that in mind. All right, you can read phase diagrams. We talked about this a little in class today. Let's just repeat a few things. Solid, liquid, gas. You basically just have to pay attention to the pressure and the temperature at which you are reading these things, because it's just going to ask you a question about what's happening at this pressure and this temperature. So, for this question, you have to say, what is the normal boiling point of this substance? Normal means STP. Our pressure is in atmospheres. So we go to 1, draw a line across, stop, and go down. I'm going to guess about 8, approximately, atmospheres. But, it could always ask you at what temperature does this sublimate if you're at a pressure of 0.02. At what pressure does this boil if you're at a temperature of 90? Stuff like that. So that's it for these tough ones. And pretty much everything else is going to be on the Castle Learning. So let me open up the field to the questions. I wish I could figure out a way to make our video output not suck.
Move closer to Manhattan.
Call Verizon until Fios exists everywhere.
Yeah, I feel like that's good.
That might work.
Well, we have numbers. Get everyone who's watching a call and ask them to put Fios in Clifton Park.
All 11 of us.
All 11.
All 11.
Call Verizon. Tomorrow's a day.
Oh, did I goof on this problem just now? I must have. No, not 8. Tomorrow is a day, yeah. What is the normal boiling point? Boiling point, Mr. G. So this is a solid. So it boils at around 80. 80, not 8. What did I do? I did the melting point. Thank you, Owen. Appreciate you catching that. So I wanted the normal boiling point. I looked at where it crossed here, which is solid to liquid, instead of liquid to gas, which, believe it or not, is what boiling is. It's all right. We all make mistakes. Degrees C. All right. Any other questions? Yeah, it's super lagged. I wish I could hardwire, but these don't have Ethernet ports.
No. Buy an adapter.
It's not on a terrible delay, but it's definitely noticeable. Hopefully I don't sound robotic. That's all I really care about.
Sounds fine on the replay.
Questions. Text me on Remind. Questions. If not, you guys are going to kill it tomorrow because you're awesome. All right, number 3. Oh, so the video just lags.
Yeah.
Or does my voice lag? Does my voice lag the video, or does my video lag with the voice? This is life's questions. I'll just do a recap of number 3. So, yeah, that makes sense. What do we do at number 3? It's a partial pressure question. So partial pressure is moles of our gas divided by total moles of our gas times total pressure, and that gives us our partial pressure of that gas. I know the moles of my oxygen was 2. I calculated the moles of my hydrogen and nitrogen to get 12 when I added it with my oxygen. Then I did 2 divided by 12. And got 0.167. Divided both sides by 0.167 and got my total pressure equal to 467 mmHgs. I should probably just get into the habit of like doing the work first and then talking. And then my work will catch up to my voice.
Now you're talking like you have voice modulation.
Because it doesn't lag like that far behind, but it's definitely noticeable. But that's okay. Any other questions? Shoot me a text on Remind. My students suggest I should stream on Twitch or Instagram. I mean, it's going to lag no matter what.
The problem with Instagram is it doesn't save it. I guess we could save it, but
Well, yeah, I'm not, yeah.
I'm also not going to sit on my phone.
No, that sounds awful. I guess you could do it on your iPad, but then you have to do the work on your phone. I don't know. I'm not a big fan of streaming it on Instagram.
Tell them to come hardwire our house.
What?
Tell them to come hardwire our house.
Well, we have a way to do the stream hardwired. We just need to buy an adapter for our computer.
Well, we could probably invest in that. We live stream enough.
Yeah. Yeah. You're not wrong.
Probably like $30.
It's probably a stupid amount of money regardless. All right, cool. Good night, people. I'll see you tomorrow. You're going to kill it because you guys are the best.